So we'll just review what was Cauchy's integral theorem and Cauchy's integral formula, and we'll move forward today. So last class, we had discussed some important concepts of, simple closed path. So closed paths that do not intersect or touch itself. So all these are the examples of simple closed path. All of these. Then closed paths that are not simple, these are the examples wherever there is an intersection or the paths touch each other. So these are not simple. So simply connected domain is a domain containing, enclosing all points within a simple closed path. So it's a domain in a complex plane such that every simple closed path in D encloses only points of D. So when we say simply connected domain, it means all points within this simple closed path, which does not have any holes or breaks in the domain. Next, multiply connected domains. Multiply connected domains are those in which there is a domain within which there is a region or even a single point where the function is not defined. So if there is only one region inside this whole outer region, so then this is called as a doubly connected domain. However, if there are two sub-regions within the overall region, and in these two sub-regions the function is not defined, then it is called as a triply connected domain, quadruply connected domain, and multiply connected domain, like that. Now Cauchy's integral theorem, very, very important theorem. If f of z is analytic in a simply connected domain, then for every simple closed path C in the domain, integral f of z dz will be 0. So the contour integral of f of z dz will be 0 in a simply connected domain. So when you across the circle, and consequence of this result is that from one point to another point, the integrals are path independent. They're path independent. Of course, if you take contours, all contours are the same, 0. Now, if you take z1 to z2, then you can go through any path. It will all be the same. The integral will be the same from z1 to z2. So in complex integrals, if you want to reach from z1 to z2, you have to integrate along from z1 to z2. You can choose any path as long as it is a simply connected domain. For multiply connected domain, the Cauchy's integral theorem works slightly differently, like we discussed for a doubly connected domain. For a doubly connected domain where there is a region where it is undefined, the function is undefined. Now there's a boundary on which the function is defined, C1, C2 is another, and you have another path C3. Now the integrals, as long as the sense, anti-clockwise or clockwise sense, are the same, the integrals, the contour integrals of the function about C1 or C2 or C3, they all will be equal, and they will not be 0 because it is not a simply connected domain. It will not be 0, it will have some value. Okay, this is Cauchy's integral theorem for doubly connected domain. For a triply connected domain, we have this C1 and C2 are inner regions where they enclose regions where there are where functions is not defined, and there is this outer uh, circle D, outer region. Now this path C, integral, contour integral of um, contour integral of the function around C is equal to the sum of the contour integrals, around C1 and C2 here. So now for a quadruply connected domain, you will get contour integral around C is same as contour integral around C1 plus contour integral around C2 plus contour integral around C3. Next, we ended here in the last class. We discussed Cauchy's integral formula. If Z is analytic in a simply connected domain D, then for any point Z0 in D and any simple closed path C in D that encloses Z0, we have integral. This is very important. See, if we have already done for integral dz by z minus z0, where C encloses this point of singularity. That is, what is the point of singularity? Where the function is not defined. So z equal to z0 is the point of singularity. So if at the point of singularity, if this f of z is 1, we have already solved this. Dz by z minus 1, dz by z minus z0 in the contour integral is 2 pi I. Now, the Cauchy's integral formula says, now integral of f of z by z minus z0 dz will be 2 pi I into f of z0. 2 pi I into f of z0. So, in other words, f of z0 can be written as 1 by 2 pi I integral, contour integral of a region circling a region that encloses z0. Okay, the path that encloses z0. That is C. So contour integral around C is of f of z by z minus z0 dz will be f of z0. So this is the Cauchy's integral formula. Now we'll have to do some problems for practice, but we begin here. Before, there's one more extension before we move forward. Now, that is Cauchy's integral formula. Now, next is derivatives of analytic function. Derivatives of analytic function. Now, this is extension of Cauchy's integral formula. If f of z is analytic in a domain D, then it has derivatives of all orders in D which are also analytic. Now, this is a theorem. We will not prove this. But what we require is the results of this theorem. The values of these derivatives are f dash z naught is 1 by 2 pi I integral f of z upon z minus z naught the whole square dz. Okay. C is of course a simple any simple closed path. Now f is analytic. Very important. F must be analytic. It cannot be that f is not analytic. F is analytic, but this function f of z by z minus z naught whole square will not be analytic. Okay. So here when square comes, you get f dash. When power 1 comes, you get f. So similarly, f double dash is 1 by 2 pi I integral closed on a closed contour C f of z by z minus z naught the whole cube. Proceeding in this way, we get nth derivative of f is 1 by 2 pi I integral over closed contour f of z upon z minus z naught whole power n minus 1 raised to the power n minus 1. So these are the derivatives where here important C is any simple closed path in D that encloses Z naught. That encloses Z naught. Okay. So these formula are important. Now on Cauchy's integral formula, we will work out some problems and on these derivatives. It will make it very clear how to solve these problems. The first one. Evaluate integral over closed path, so contour integral of e power z by z minus 2 dz, where C is a contour enclosing z equal to 2. So I'll write the Cauchy's integral formula once here, but for each problem I'll not repeat. So using Cauchy's integral formula, what is it? Integral on a closed contour, the f of z by z minus z naught dz will be f of 2 pi I times f of z naught. So therefore, we get integral e power z by z minus 2 dz is 2 pi I times e power 2. What is z naught? Z naught here is 2. All right. So numerator is f. So 2 pi I e square. Now, sometimes they are asked, value is also asked. So 2 pi e square, let's say e square times 2 into pi. So you get 46.426 or 4268. So you get up to second decimal if you restrict 46.43. So this is the value of the integral. Just direct use of Cauchy's integral formula. How to evaluate this integral. Next. Question 2. So evaluate contour integral z cube minus 6 upon 2z minus I dz, where C is a contour, simple closed contour, enclosing z naught equal to I upon 2. So solution. So we have to evaluate this integral. Now z cube minus 6 by 2z minus I dz, we will make small changes. Z cube minus 6 upon, take 2 common, 2z minus I upon 2 dz. This is C. So this becomes, you take half outside. Now it is in the Cauchy's integral formula form. Your z naught is I upon 2. Here, z naught is I upon 2. So this is half 2 pi I times f of z naught. What is f? The numerator, z cube minus 6. So you get pi times I into z cube. Okay, I'll write here z cube minus 6 for z equal to I by 2. So pi I into z cube is I cube by 8 minus 6. I cube is minus I. So taking this inside, pi I minus I whole square. So sorry, minus I square, not minus I whole square, minus I square. So minus of I square. I square is minus 1. So minus I square will become plus 1. So you get pi by 8. And take this inside, minus 6 pi I. Okay. So this is the answer. I will write the next problem. Next, evaluate. This is an important question. Evaluate integral on the closed path z square plus 1 upon z square minus 1 dz. Okay, where c is a counterclockwise path given by. Now there are three problems here. The first bit, a bit, modulus of z minus 1 equal to 1. B bit, modulus of z plus 1 equal to 1. C bit, modulus of z minus I equal to 1. All are circles. Okay. All are circles. Now let us evaluate this one. First one. C is the path given by modulus of z minus 1 equal to 1. That means center at 1, 1, 0, and radius equal to 1. Now, therefore, I integral, we have to evaluate now, closed path C, z square plus 1 by z square minus 1 dz. So now, how we'll do? We will write this as z square plus 1 by z plus 1 into z minus 1. So what is the singularity? Here z naught is equal to 1. Here z naught equal to 1. So now the way we write is z square plus 1 by z plus 1 divided by z minus 1 dz. So this is the singularity. This becomes your function f of z. And this is analytic because, at z equal to 1, this is analytic. It doesn't go have a singularity. So here, again, f of z is z square plus 1 by z plus 1. And z naught is equal to 1. So according to the Cauchy's integral formula, this will be 2 pi I into f of z naught. So this is 2 pi I times 1 square plus 1 by 1 plus 1. So 2 by 2, 1. So answer is 2 pi I. 2 pi I. This is the answer for the first case. Now let us look at the second case. C is a path given by mod z plus 1 equal to 1. So in the Argand's plane, This is not I, yeah, this is 1. So this is 1, this is -1. Okay. Now the circle, I will, okay. So this is the path. Now this is the singularity point here. Okay. Now let us evaluate this integral. Integral closed path z square plus 1 by z square minus 1 dz. Now z is minus z naught equal to -1 is this point of singularity. So let us see how we write. I will write this as z square plus 1 by z minus 1 upon z plus 1. So z square minus 1 I have written as z minus 1 into z plus 1. Z minus 1 I have taken up. Z plus 1 I have kept down. Now this is the point of singularity. Now here f of z is z square plus 1 by z minus 1 and z naught is -1 here. So by Cauchy's integral formula, you get 2 pi I times f of z naught. This will be 2 pi I. So -1 the whole square plus 1 by -1 minus 1. So numerator is 2, denominator is -2. So you get minus sign. So you get -2 pi I. This is, so when the path changed, the value of integral also changed. Okay. Next. C is a path given by modulus of z minus I equal to 1. So let's use the same figure. Change the color. I will be here. Okay, this will be the path, closed circle path. Circle with the center at I and radius 1. Okay. So for this closed contour, z square plus 1 by z square minus 1. If we observe this, the 2 points of singularity, z equal to 1 and z equal to -1, they don't come within the circle. There are 2 points of, non-singularity here. So this is 1 and this is 1. 2 points of singularity, not non-singularity, 2 points of singularity. So at z equal to -1 and z equal to 1, the functions are not defined in this particular one. However, in this contour, you are not getting these points. So now this is a simply connected, this contour has all points here within this circle. This entire function is defined. So there is no problem. Thus, according to the Cauchy's integral formula, the answer to this will be 0. Only if there is a singularity, then it's a problem. So this answer to this is 0. Okay. Now I will add one more. C is a path given by mod z is equal to 2. If I do this, can any one of you tell me the answer? I'll give you 2 minutes. Think. Look at the figure and think. I need to evaluate this integral. Please tell me. Any answer? Okay, look at this. Look at this solution now. Now this, you know, this path is C, mod Z equal to 2. Okay, it has the center at the origin and radius equal to 2. This is 2, this is 1, this is -1, this is -2. This is real axis, this is imaginary axis. So this path is mod Z is equal to 2. All right. Now what about these paths? This is modulus of Z plus 1 equal to 1. Center -1, radius 1. How about this path? This is mod Z -1 is equal to 1. Center 1, radius 1. So let's say this is C1 and let's say this is C2. C1 and C2. So this, now this is a multiply connected domain. This is a multiply connected domain. So in fact, this is a triply connected domain. Here there is a point, one point of singularity, another point of singularity. So we can write this as integral C1 z square plus 1 by z square minus 1 dz plus integral C2 z square plus 1 by z square minus 1 dz. Now for C1, we got the answer here minus 2 pi I. And for C, we have already got the answer 2 pi I, the same. So you get minus 2 pi I plus 2 pi I from the previous condition. So the integral is 0. Okay. Is this clear? Is this clear? I'm not getting your. Okay. So this is Cauchy's integral formula for multiply connected domain. So this problem is an important one. Problems come like this. So you need to practice this one, the third one. First two were just very basic. Next. Question 4. Evaluate integral, closed contour integral of tan z upon z square minus 1 dz around the circle mod z equal to 3 upon 2. Now we have to note that tan function is not defined. Tan z is not analytic for or at z equal to plus or minus pi by 2, plus or minus 3 pi by 2, plus or minus 5 pi by 2, so on. But then if we look at the circle, Okay, this is the circle. Z equal to 3 by 2. 3 by 2 is 1.5. So this particular point is 1.5. This is 1 minus 1 minus 1.5. The value of pi is 3.14. Pi by 2 will be 1.57. Now 1.57 lies outside. Okay. Pi and minus pi lie outside the. So none of the points. So, however, none of these points lie within the circle. So within the circle, tan z is analytic. Within the circle, tan z is analytic. Okay. Now, but 1 by z square minus 1, which is 1 by z minus 1 and z minus z plus 1. Okay. Have two singular points. Have 2 points of singularity. Z is equal to 1 and z equal to minus 1, both of which lie within the circle. So then what do we have to do? So take another path, any circular path. The answer will be the same. C1, C2. This path is C. Okay. So just like we did the previous problem. So therefore we get, by Cauchy's integral formula for multiply connected domain, integral tan z by z square minus 1 dz is integral C1 tan z by z minus 1 into z plus 1 plus C2. Now this now C1 is this path, okay, where center is at minus 1. Okay, center is at minus 1. So what we will do, we will write this as tan z upon z minus 1 upon z plus 1 dz plus integral C2 tan z upon z minus z plus 1 upon z minus 1 dz. For this path, the point of singularity enclosed is z equal to 1. Here the point of singularity enclosed is z equal to minus 1. So now this becomes 2 pi I f of z naught equal to -1 plus 2 pi I will write f1 here, f2 into z naught equal to +1. Okay, by Cauchy's integral formula. 2 pi I tan of -1 by -1 -1. Okay, plus 2 pi I tan 1 by 1 plus 1. Okay, f2 is this function. So here we have to put 1, 1. So tan 1 by 1 plus 1. Here we get tan of -1 by -1 -1. So we get 2 pi I into tan 1 upon 2 plus 2 pi I into tan 1 upon 2. So this will be 2 pi I tan 1. This is the answer. This is the answer. Okay, next question. Okay, is this clear? How we evaluate? This question 3 and question 4 are important. We just practice this. You will get a full idea of how to evaluate. Next, problems on higher derivatives. Problems on higher derivatives. So this is the fifth one. Evaluate integral over closed path cos z upon z minus pi I whole square dz. Okay, where C is a contour enclosing z equal to pi I. So let's look at the solution now. Now this is 2 pi I times f dash z, because this is square. Here, look at the formula that we gave today for derivatives here. F of z by z minus z naught whole square contour integral will be 2 pi I times f dash z naught. So by Cauchy's integral formula, this one will be this I integral cos z by z minus I z minus pi I whole square dz is 2 pi I times the first derivative of cos z at z equal to pi I. F dash z naught, right? This is f dash z naught term. Now, this one will be 2 pi I cos, derivative of cos is minus sine. So we get minus sine z, z equal to pi. So we get minus 2 pi I sine of pi times I. Okay. So you can leave it here, or we use sine of I times Z is minus sine hyperbolic pi, hyperbolic Z. We can use this result that which we had derived earlier. So depends on the question how it is given. So this will become 2 pi. No, this is I times. Yeah, I times sine Iz. So this will become sine hyperbolic pi. Okay. Of course, you can leave it here and give the answer. Depends on what is the answer given in the options. So this is how we find this one. Now let's do the next one. Similar, very similar question. Now evaluate integral z power 4 minus 3z square plus 6 upon z plus I the whole cube dz. This is easy. For any contour enclosing z naught equal to minus I. So this is the point of singularity, and then this is cube here. So the solution I closed interval C z power 4 minus 3z square plus 6 upon z plus I the whole cube dz is equal to, this is cube, so second derivative 2 pi I, the second derivative of the numerator at, okay, z is equal to minus I. So let's do this. So differentiate it twice. So first derivative is 4z cube minus 6z. Second derivative is 12z square minus 6. So this is 12z square minus 6, z equal to minus I. So 2 pi I times 12 into minus I the whole square minus 6. So minus I whole square is I square, which is minus 1. So minus 12 minus 6 is minus 18. Minus 18. Oh, just a second. I made a big mistake here. I'm sorry. In this problem, very sorry, this is comes in Taylor series. I made a mistake in this problem. Here, this will be 1 factorial. Here it will be 2 factorial. Here it will be n factorial. Please rectify. Okay, here will be n factorial. So this is 2 pi I by 2 factorial you will get here. By 2 factorial by 2 factorial. 2 factorial is 2. You will get minus 18 pi I as the answer. Minus 18 pi I. So this is how we do derivatives. Please rectify that formula. I missed. Okay. So with this, we complete, problems on Cauchy's integral theorem. Very important. Next is okay. Next is series expansions, power series, Taylor and Laurent series. Taylor and Laurent series expansion. So series expansions, complex series expansions. So first one, power series. Now, power series in powers of Z minus Z naught, that is power series about Z equal to Z naught, okay, is of the form sigma n equal to 0 to infinity an into Z minus Z naught to the power n, which means when you substitute n equal to 0, you get a naught plus a1 times Z minus Z naught plus a2 times Z minus Z naught the whole square plus the kth term ak into Z minus Z naught whole power k, and it goes to infinity. Now Z is a complex variable, of course, and where a naught, a1, a2, a3, so on are complex constants or complex coefficients of the series. Okay. Now, Z minus Z naught or Z equal to Z naught is called as the center of the series. So this is power series expansion about the center Z equal to Z naught. This is how it is defined. And when z not equal to 0, power series expansion about the origin, you will get an, put z equal to z naught, you will get a simple one. Now, next one, Taylor series. Taylor series expansion of a function f of z. Okay. Now, very important note is for Taylor series to be defined, f of z must be analytic about the center of the series z equal to z naught. Okay, very important note this is. Then, now Taylor series is defined as of f of z is defined as, just as we have in real numbers, f of z can be written as an infinite series of an into z minus z naught whole power n. It looks like the same as the power series expansion. However, very important, where an is 1 upon n factorial into the nth derivative of f at 0, at z naught, at z naught. So here, how does this Taylor series look? This, now this will be equal to a naught plus a1 z a1 by 1 factorial z minus z naught plus a2 by 2 factorial z minus z naught the whole square plus a3 by 3 factorial z minus z naught the whole cube up to infinity. So this is the Taylor series expansion, where important, now an is 1 by n factorial nth power of z naught, nth power of nth derivative of f at z naught. Now by the Cauchy's integral formula for derivatives, we get n factorial by 1 by 2 pi I times integral over a closed contour of f of z by z minus z naught whole power n plus 1 dz. Okay. This is the Taylor series expansion. This is Taylor series for f. Now, if z z naught is equal to 0, that is the center. Then Taylor series is called as Maclaurin series. Okay. So this is the Taylor series expansion. It's just like our real for Taylor series for real functions. Up to here, up to this step, you know, it is the same. Okay. Here, instead of here A1 in real functions is, this is F, no, F dash, F double dash, F triple dash, so on. So here also, I'm sorry. Here I should not write this because I'm including this factorial here. I should not be writing this. I'm including this factorial terms in the within the coefficient itself. Okay. There in real functions, we get f dash by 1 factorial, f dash by 2 factorial, f dash by 3 factorial, and so on. And this a naught will be actually f naught, f of z naught, basically. So now only difference here is here our evaluation of the derivative has the complex integration involved. F of z by z minus z naught whole power n plus 1 dz over this contour integral. This contour should be any closed path which encloses z equal to z naught. So then that is the Taylor series. Now, very important, the third part, Laurent series. Now, if f of z itself has a singularity at z equal to 0, then Taylor series cannot be used. Cannot be used because you cannot differentiate. Function has to be analytic. So then here what the series that we include is called as the Laurent series. So f of z instead is represented by Laurent series. Laurent series as below. Okay. So now the function has some point of singularity. So let us say you have two, there's a closed path and there is a point of singularity here, z naught. Now around this we take one path. So this path, let's say external path is C1 Internal path is say C2. Now what we have is this path has a singularity, and between these two paths, the function f of z is analytic. Okay, f of z is analytic in this annulus. So now we will choose a path a closed path circulating this z naught, and this is a path C that we choose. Okay. Now keeping this in mind, now we will define the Laurent theorem. Laurent theorem for defining the Laurent series. Now, if f of z is analytic on two concentric circles or contours with center at z equal to z naught, and in the annulus between them. So f is analytic on the circles C1 and C2 and in between them. Okay. Then f of z can be represented by the Laurent series as very important, f of z is sigma a power n, sorry, a n to z minus z naught whole power n equal to 0 to infinity, plus sigma n equal to 1 to infinity bn bn upon z minus z naught to the power n. This ensures, see, this part is the usual Taylor series expansion, the first part. The second part has z minus z naught in the denominator. So it gives idea of the singularity. This gives the idea of singularity. With z equal to z naught, you substitute, function will not exist. So when function is not analytic, we should remember, so far what we have discussed is function is analytic. So if the function is not analytic at z equal to z naught, Taylor series cannot be used. Laurent series has to be used like this. Now this part with the negative powers of z minus z naught, this is called as the principal part of the Laurent series. This is the principal part of the Laurent series. So now we have to still define what is an, where an 1 second. There is, uh, it should be this. An is n factorial. Yeah, it should be this. 1 by n factorial f dash, f nth derivative of z naught, which is same as 1 by 2 pi I, 1 by 2 pi I into integral f of z by z minus z naught whole power n plus 1 dz. Now Bn will be similarly. Now how Bn is defined is slightly different. 1 by 2 pi I, this is just like the Taylor series, but this is 1 by 2 pi I integral over closed path. You get z minus z naught to the power n minus 1, z minus z naught to the power n minus 1 times f of z dz. Okay. Now here, this from the denominator, we have removed this. And now very important, where C is any simple closed path that lies in the annulus between the between the two circles. Yeah, this is the one. This is the Laurent series. Now together we can write the Laurent series like this. This is much easier to remember. It covers all. Alternatively, the Laurent series can be written as of course there is advantage of doing into two parts here. One is positive powers of n, other is negative powers of n. However, this is another method where f of z can simply be written as n equal to minus infinity to infinity, not 0 to infinity, minus infinity to infinity, an to z power z minus 0 whole power n. This takes care of all the powers. An will be 1 by 2 pi I times integral f of z by z minus z naught to the power n plus 1 dz. Now n takes all integers values. N belongs to z, all integers, set of integers. Okay. However, there's a trick in problem solving. There's a trick in evaluating the Laurent series. We don't have to go by writing all these formulas. But the definition, we should know that this is what Laurent series is. If we, so problems. Hmm. First one, f of z is sine z by z power 5. Find the Laurent series of f of z about z equal to 0. Very simple. So this is about z equal to 0. You just write Maclaurin series of sine z. Okay. Now about z equal to 0, the Maclaurin series of sine z is sine z is, we know that this is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. Okay, this is just the series expansion of sine function. Same. Now, therefore, 1 by z power 5 times sine z. If we do, we'll get 1 by z power 4 minus 1 by 3 factorial times z plus 1 upon 5 factorial minus z square upon 7 factorial plus z power 7 by 9 factorial and so on. This goes on. This, okay. Now this is the Laurent series expansion straight away. Straight away, very simple. If we actually write these terms and evaluate, we will get the same result. We can try it. Okay, we can try it, but there's no point. So here you will get 2 pi I by n factorial into f dash z, f double dash z. You will get the same result. So easy way to write the Laurent series expansion. Second question. Find Laurent series expansion find Laurent series expansion of z square times e power 1 upon z with center z equal to 0. Now, problem is not with z square, problem is with e power 1 by z. At z equal to 0, it is undefined, so there is a point of singularity. Okay. So how to find? Very simple. We know that e power z is equal to 1 plus z upon 1 factorial plus z square upon 2 factorial plus z cube upon 3 factorial. This is the very standard series expansion of e power z. We know this from calculus. Now, therefore, e power 1 by z, replace z by 1 by z here. 1 plus 1 by z plus 1 by 2 factorial z square plus 1 upon 3 factorial z cube plus 1 upon 4 factorial z power 4, so on. Now multiply this with z square. Z square times e power 1 upon z, multiply with z square, you will get z square plus z plus 1 by 2 plus 1 upon 6z plus 1 upon 24 z cube z square, so on. This is the Laurent series expansion. Okay. Okay. Now this one is an important problem. Expand 1 by 1 minus z in a non-negative powers of z and b negative powers of z. So now this so much depends on what the value of z is. Okay, this is from the series, geometric series concept, we know that. So the first case, now if modulus of z lies between 0 and 1, that means z takes small values, then this is 1 by 1 minus z can be written as 1 minus z whole power minus 1 and write the binomial expansion. Okay, the binomial expansion for this is 1 plus z square plus z cube plus z power 4, so on. Okay, this is simple. This is what a by 1 minus r, right? This is sum to infinite, sum to infinity of a geometric progression, where the first term is 1 and the common ratio a by 1 minus r. So common ratio is z. So you get 1 plus z square plus z cube, so on. Or you think of this as 1 minus z whole power minus 1, binomial expansion for negative integers. You get this one. Now case 2. Now if mod z is greater than 1, then we cannot use this formula is applicable only when mod z is less than 1. Common ratio should be less than 1. Only then we can do this. Then we will write this expansion like this: 1 by 1 minus z we divide by z both numerator and denominator. Now what happens is 1 upon mod z lies between 0 and 1. Okay. So what we do, take the minus sign. So this is minus of 1 upon z times 1 by 1 minus 1 upon z. This is now a by 1 minus r, where this r 1 upon z lies between 0 and 1. For this, we can write the same expansion as above. Just replace z by 1 by z. So we get 1 plus 1 by z plus 1 by z square plus 1 by z cube, so on. When you multiply, we get minus 1 upon z minus 1 upon z square minus 1 upon z cube. So this is how we expand the Laurent series. Okay. Very important problems for consideration and practice. Basic one. Now find all Laurent series expansions of 1 upon z cube minus z power 4 with center at origin. Now this f of z is 1 by z cube into 1 minus z. So this is just your previous problem. There are two cases. Now we have to do about origin. The previous one was also about the origin only. So now if mod of z lies between 0 and 1, then f of z is 1 by z cube times 1 plus z square plus z cube infinity. Now this will be 1 by z cube plus 1 by z. Yeah. Plus 1 z cube. Oh, I missed one term here. That's what I was wondering. 1 plus z. 1 plus z square plus 1 plus z plus 1 plus z square times infinite. This is the first series. Now, if mod z is greater than 1, then f of z is 1 by z cube for sure, then multiplied by the previous series here, minus 1 by z, minus 1 by z square, minus 1 by z cube. So we get minus 1 upon z power 4 minus 1 upon z power 5. So we see how to expand Laurent series without using formula, just by simple tricks. All you need to know is basic series, geometric series expansions. Another important one, find all the Laurent series of. Now this is a different question. F of z is minus 2z plus 3 upon z square minus 3z plus 2 with center origin. Now first thing to do is look at this minus 2z plus 3 by z square minus 3z plus 2. Try to write this in terms of partial fractions. So find a and b. How will you find? 2z plus 3 is equal to a times z minus 2 plus b times z minus 1. When I bring this to a common denominator, I get a times z minus 2 plus b times z minus 1. That should be equal to the numerator. So put z equal to 1. We get minus 2 plus 3 is 1, is a times 1 minus 2 is minus 1, b times 0. So a is equal to minus 1. Now put z equal to 2. We get minus 4 plus 3 minus 1 is a times 0 plus b times 1. So we get b is equal to minus 1. So a and b both are minus 1. Therefore, this one we can write f of z as minus 1 upon z minus 1 minus 1 upon z minus 2. Now, what are the poles? Now, the poles are 1 and 2. These are the poles. Now we have to expand about 0, but 1 and 2 are the poles. So if we have to expand about 0, 0 is no problem. Okay, 0 is not a problem. But these are the problems, 1 and 2. So we can do an expansion such that one of them is included. So Laurent series expansion, the possible expansions are these. First one, that modulus of z lies between 0 and 1. Why I'm choosing modulus of z? Because I want um, I want to expand about z equal to 0. So this means, with pencil I'll draw here, this is a circle. So it does not include any of the analytic non-singular singular points. There are points of singularity, it doesn't include. Next, another one is when you have to, the circle can be like this. That means there is one point of non-singularity. Third, when mod z is greater than 2, there are 2 points of non-singularity in that particular case. Okay, this is case A, this is case B, this is case C. So let us expand one by one. Mod z lies between 0 and 1. Then now f of z is 1 minus z plus 1 by 2 minus z. Okay, z minus 2. So I have taken this minus sign inside. 1 by 1 minus z, 1 by 2 minus z. So now I will slightly change this. 1 by 1 minus z plus, I will take 2 outside. 1 by 1 minus z over 2. So now this is a by 1 minus r, a by 1 minus r. So two geometric series. The first one is 1 plus z square plus z cube, so on up to infinity. Second one is half a, first 1 plus z upon 2, because r, the common ratio is z upon 2, by z square by 4 plus z cube by 8, so on. So now when you add this, okay, z square, z cube, let us collect the terms. This is 1 plus half. Now z term is 1 plus 1 by 2 square, then 1 plus 1 by 2 cube, 1 plus 2 power 4. Of course, we can write this as summation of 1 plus 1 by 2 power n plus 1 times z power n equal to 0 to infinity. Okay, so this is not a Laurent series, it is Taylor series expansion. You don't get a Laurent series, means residues must be there. Around 0 there are no residues, so no problem. So we can write this as 3 by 2 plus 4 plus 1, 5 by 4 z plus 8 plus 1, 9 by 8 z square. 17 by 16 z cube, so on. This is the series expansion for first case. Now let's consider the second case. Modulus of z lies between 0 and 2. Modulus of z lies between 0 and 2. So here, sorry, between 1 and 2. So f of z we have written as 1 by 1 minus z plus 1 by 2 minus z. Now, because z is greater than 1, 1 by z, in this case, 1 by z will be lesser than 1. So we will have to do an expansion like this. Divide by z as we have done earlier. You just have to think of how to expand. Okay, that's all. Now, because 2 by z, because z is less than 2, this will be greater. Okay, you need not do this one. Now z by 2, okay, yeah, 1 by z will be less than 1 for sure. But 2 by z will be greater than 1. Okay, or z by 2 will be lesser than 1. So the way we write is like this. The second term we will write as it is 1 by 1 minus z by 2. Because for this condition, z is greater than 1, so reciprocal will be less than 1. So I have brought this term less than 1. But z is less than 2, so z over 2 will be already less than 1, so I don't have to do any changes for that. So now we will write it in this form. 1 by z with a minus sign, 1 minus 1 minus 1 by z. This is again sum to infinite terms of a geometric series. A by 1 minus r. So we get minus 1 by z into 1 plus 1 by z plus 1 by z square plus 1 by z cube infinity plus a by 1 minus r. This is 1 plus z over 2 plus z square upon 2 square plus z cube upon 2 cube to infinity. Let's simplify further. You get minus 1 by z minus 1 by z square minus 1 by z cube minus 1 by z power 4 we can combine, or we can just leave it like this, because this will go to higher and higher negative powers. This will go higher and higher positive powers. Okay. So with the negative parts, this is the principal part of the Laurent series. Okay, in the previous case, the principal part doesn't exist, so it becomes the Laurent series becomes the Taylor series. However, now here, third case, mod z greater than 2. So 1 by z will definitely lie between 0 and 1, and 2 by z also lies between 0 and 1. Okay, in this particular case. Therefore, f of z is, 1 by 1 minus z plus 1 by 2 minus z. Now, here for both cases, we have to divide by z. Oh, here I think I've missed. I made a mistake here. This should be half. Now here, this we divide by z this time. So minus 1 by z times 1 by 1 minus 1 over z minus 1 by z times 1 by 1 minus 2 over z. Now let's expand. Hmm. 1 plus 1 by z plus 1 by z square minus 1 by z by 1 plus 2 over z plus 2 square by z square plus 2 cube by z cube we have common terms, so we can add now. So if we add, we get minus of 2 by z plus 1 plus 2 by z square plus 1 plus 2 square by okay, 1 plus 2 square by z cube plus 1 plus 2 cube by z power 4 so on. Of course, we can leave it here. Minus 2 by z minus 3 by z square minus 5 by z cube minus 9 by z power 4 so on. Okay. All right. So this is Laurent series. There's a very small part that is left, that is residue theorem and residue integration method. With that, we complete this unit, but residue theorem and residue integration is important because they ask simple questions from that. And residue theorem uses the Laurent series one particular term. So I'll cover this tomorrow and complete the problems on complex integration. We will do problems from the previous year GATE papers. Okay, thank you. I will stop here for today.